Ladies and gentlemen, I'm in between you, the session, you and the cocktail hour, which is always a dangerous place to be. But please stay on and be attentive for the next 20, 30 minutes. I'm not saying that we kept the best to the end, because we had a wonderful, inspiring program today. But what is coming now is also worth looking to and listening to. My name is Lucas Noldes. I'm a member of the Netherlands Academy of Technology and Innovation and the current chair of the CAETS Communication Committee. The CAETS Communications Committee was set up to find ways of helping the member academies improve the communications of policy, educational initiatives, and the importance of engineering and technological sciences in society. The aim is to amplify our impact on governments and the general public of the countries in which we live by communicating the important role of technology in society clearly and effectively with a general audience. CAETS wishes to encourage technological scientists and engineers around the world to effectively communicate in a simple and engaging manner with general audiences, with a focus on young people and students. This is done through a competitive selection of short videos of no more than 5 minutes in length, explaining the societal importance of technological breakthroughs and engineering successes. Such videos have a dual aim of, 1, inspiring students to follow careers in engineering and technological sciences, and 2, educating the general public on the impact that engineering and technological sciences have in their lives and future. The annual CAETS Communication Prize was established to recognize the best of such videos from member academies globally. This is awarded to the most outstanding audiovisual communication of excellence and innovation in technological sciences or engineering. The winning entry will have clearly communicated the successful identification of and solution for a problem, with the outcome being of benefit to the economy or society, either nationally or internationally. This year, we received 12 nominations from 10 countries: Argentina, Australia, China, India, Korea, Netherlands, South Africa, United Kingdom, United States, and Uruguay. These were evaluated by a judging panel consisting of the chair and deputy chair of the CAETS Communications Committee and representatives of member academies currently serving on the CAETS board. The entries were ranked against the following criteria. 1, the winner should have clearly targeted at a general, non-technical audience with a focus on inspiring youth and student segments. 2, plain language, intelligible to a general audience. The video must clearly explain why the problem is important before describing the nature of the solution. 3, articulating an innovation that solves a meaningful problem using technology, either globally or locally, and highlighting successful practical application where relevant. And 4, it must be credible and verifiable. The submissions were of outstanding quality, and it was not an easy task for the judging panel to come to a final ranking. The judging process resulted in a winner and 2 honorable mentions. The honorable mentions are, and now we should display the first slide of the top one. Yes. Yes, that's correct. Marjolein Helder from the company called Plant E in Wageningen, the Netherlands, with a presentation video called Plant Power for Carbon Negative Energy Production, nominated by the Netherlands Academy of Technology and Innovation. I'm most likely the only Dutchman in the hall, so I will take this certificate for honorable mention home and hand it over to Marjolein. The second honorable mention goes to Richard Hopkins of the University of New South Wales in Sydney, Australia, for a video called The Sunswift Guinness World Record, nominated by the Australian Academy of Technological Sciences and Engineering. Do we have a representative of ATSI in the room right now? Why, that comes close. So I'd like to hand over this to you, Cass. Please take this home and hand it over to Richard when you get home. Okay, and give him a hand. So, but the winner is, the one and only winner, is Dr. Caitlin Howell of the Department of Chemical and Biomedical Engineering of the University of Maine in Orono, United States. Nominated by the US National Academy of Engineering for a video entitled Deciphering Nature's Secrets, Bio-Inspired Solutions for Antibiotic Resistance. I'm going to, before we invite Dr. Howell to the stage, I'm going to read a bit more about her. Dr. Howell received a bachelor and a master degree in biology from the University of Maine and completed her PhD in physical chemistry at the University of Heidelberg in Germany. She then went on to Boston to work as a Technology Development Fellow at the Weiss Institute for Biologically Inspired Engineering, part of Harvard University, where she focused on developing and translating bio-inspired technology to the market. In 2016, she returned to the University of Maine as a faculty member to set up her own lab, the Howell Biointerface and Biomimetics Lab. Inspired by nature, Dr. Howell's group works to understand and ultimately control biological systems through surface interactions and other environmental factors. She looks to guide the interactions of biomolecules, microorganisms, and cells using non-toxic, non-invasive, surface-based methods to accomplish specific goals. Her work can be applied to medicine, to industry, and to the home. Through the development of these technologies, she also strives to understand the basic science behind biological surface interactions to provide a basis for future technologies and applications. Professor Howell's success story is a very inspiring and clear example of how engineering can help to tackle a growing problem in medical and veterinary practice, antibiotic resistance. Not by applying ever more antibiotics, but by preventing infections to occur. The jury was enthusiastic about the professional video and storytelling with good language for a non-technical audience, inspiring for both laymen and students. We liked the lively combination of an engaging speaker, professional video shots, visualizations, and animations. The problem and its implications are clearly and informatively defined using a vocabulary that requires no prior knowledge of the topic. The video continued this theme all the way through linking the solution back to the problem. It articulates an innovation that solves a meaningful problem and highlights a successful practical application. The solution is well presented and explained. It hits all the right notes. The judging panel was unanimous in its decision to award the CAETS 2023 Communication Prize to Dr. Caitlin Howell. On behalf of the CAETS Communications Committee, I'm pleased to congratulate Dr. Howell with this achievement. And I now invite Dr. Howell to come to the stage and to receive the award certificate. So, Dr. Howell, Caitlin, congratulations for this wonderful achievement. And let's show this to the photographer. That will make a nice press release. So now let's have a look at what this is all about, because for some of you the description may still be a bit cryptic. Now I'm going to try to play the video.
Bacteria are around us all the time. Most of the time we don't really notice them because they're way too small to see and they don't bother us. But we've all had an ear infection, strep throat, a UTI. These are things that are familiar across the world. Luckily for us, we have antibiotics. Unfortunately, these medicines are starting to not work as well as they used to. The problem isn't confined to just human medicine. Antibiotics are widely used in raising livestock, where they can go out into the environment and contribute to resistance there as well. These practices are projected to increase over the coming years. So, are we simply doomed to go forward into this future? No. We're human beings. We solve problems, and engineers have a critical role to play here. We are the ones who build new solutions, who take problems like this and discover how we can address it. think about a natural, beautiful landscape, if you will. And if you really start to think about it, you'll realize that bacteria are everywhere. Yet in these situations, at no point is nature hitting everything with antibiotics across the board. Maybe there is information that we can gain from this, and maybe we can take that information and turn that into solutions for human problems. In our group at the University of Maine, we focus on bio-inspired engineering of materials. And we know that a lot of problems with bacteria really start when bacteria stick to things. So if we look at nature for an example of how nature has solved the infection situation that we're dealing with, maybe our best example is us. If you think about us and the place in our body where nature does the best controlling of bacteria is actually the place where the bacteria concentration is highest, in our intestines. It's all kept in balance when we're healthy. But at a very base level, one of the most important components is mucus. Mucus is an amazing material. At a fundamental level, it's basically just acting as a physical barrier. It is presenting these bacteria with a surface that is soft and moving and flowing and dynamic. So we asked ourselves, what if we just replicated that component? Could we get towards finding that balance that nature achieves? The answer, it turned out, was yes. We could fairly easily create a mucus-mimicking system by adding a biocompatible liquid to a very commonly used solid, silicone rubber. And we found that when we did, indeed, we were able to create a mucus-like system. And importantly, we could treat any kind of medical device that was made out of this material. And we were actually able to introduce a fluid dynamic component to that simply in the form of a biocompatible liquid that would get in between those molecules in the material. When we did this, what we were doing was giving that material a mucus-like sort of surface. So in fact, we found that we could treat any type of medical device made out of this silicone rubber material. Urinary catheters are among the most commonly used medical devices. Unfortunately, due to the nature of where they are located, they're also one of the most prone to infection. We sent these materials to collaborators who specialize in catheter-associated urinary tract infections, and the results were jaw-dropping. We found between a 90 and 100% reduction in the bacteria that were able to stick to these materials, grow, and then spread to other organs. We weren't satisfied with stopping there, though. One thing that makes natural materials so amazing is their ability to change and adapt. We used 3D printing to engineer a vascular network within our silicone rubber materials. And we found we actually had created a system that would allow us to communicate with bacteria. So we were able to listen to the bacteria. When they grow and reproduce, they create compounds, and those compounds diffuse down from the surface into a liquid that we use to fill our vascular channels. But it went further than this. We actually found that we could infiltrate those vascular networks with materials that would instruct the bacteria to do specific things. So in this way, we were able to create a communication loop with the bacteria in a way that is approaching how nature handles it. We believe that being able to communicate with bacteria in this way, in real time, is going to give us a new set of tools for being able to look at bacteria as a potential partner in health and well-being for humans. Nature has evolved over millions of years to achieve balance with these organisms, and now we are working to engineer a part of that balance into human materials and processes.
So now we've seen Dr. Howell on screen, we've heard her on screen, but she's here live in front of us, and she's now going to present a few slides with a bit more in-depth information of how this beautiful invention of her works. And then over dinner you can approach her for questions. She'll join us for dinner, so we look forward to what you're going to tell us now and for the discussion we will have afterwards.
Great. Thank you so much, Lucas, for that kind introduction, and thank you very much to the committee for this award. We are very, very grateful and humbled to receive it, and we're so happy for the opportunity to share this with all of you. So I say we because I'm not that great at making videos. It was my face you saw up there, but in fact, this was a huge team effort. I had two fantastic producers, Luke McKinney and Holland Haverkamp, who really helped me to communicate this message well. We also had significant support from the National Academy of Engineering at the US, particularly Eileen Erickson and Sabrina Steinberg, who helped us put on the final touches and submit it. Also, for those of you who aren't familiar with the state of Maine, we are one of the smaller states of the US, but I've put us up there in the map. We are in the corner right next to Canada, and we have a lot of beautiful nature all around us. So I'm very happy for this opportunity to tell you a little bit more because 5 minutes goes by so quickly, but I'm very excited about this work. But before we begin, I just want to take us all a little bit to high school biology and do a quick refresher about why we're here. So I'm going to tell you how to make antibiotic-resistant bacteria. So you start out with a population of mostly green bacteria, but the beautiful thing about natural materials is that they're made up of DNA, which means there's variation in every single cell. And some of our cells here are just a little bit purple. Now, we don't like green bacteria. We want them to go away. So we use green bacteria antibiotics, and they work beautifully, right? Most of the green bacteria go away. But we can't really kill all of them completely. There's still a little bit of purple bacteria, so we wait a while, and suddenly we have the bacteria back again. Now, we can't see these, so we don't realize that now we're looking at a population of more purple bacteria, and so we hit this population again. And slowly, over time, little by little, we end up with an antibiotic-resistant purple strain. Now, you may be saying, well, where does this actually happen? Well, it's happening all around the world all the time. So a patient starts to feel sick and goes to a doctor and gets some antibiotics and takes a few of those antibiotics and then feels great and says, wait a minute, I feel great. Why take medicine if you don't need it? I'm not going to take any more antibiotics. Antibiotic resistance. What about that farmer who realizes, well, if I put a little bit of antibiotics in my chicken feed, I can get fatter chickens, because if you kill the bacteria in your chickens, the food that you feed the chickens goes to making more chicken and less bacteria. Antibiotic resistance. Then all of this leaks out into nature, as I said in the video, and starts to affect the bacteria populations there. More antibiotic resistance. Folks, this is a huge problem that we're going to be facing pretty soon. Nobody wants to go back to the time where a cut finger could mean a death sentence. So we've got to step up, and it's going to take everybody, all hands on deck, all different approaches, and there's not going to be one single solution to this. But as you heard, in our group, we're taking the approach of looking to nature. So I talked a little bit about how we're using inspiration of us, and I hope you all realize that you are superorganisms. You are made of at least as many bacterial cells, if not more, than you cells, and they make up a big part of who you are. And within you, your body is keeping those bacteria in balance using a lot of different strategies, but one of the most effective is this mucus layer. Now, I love this picture. I didn't take it. This was actually done by a researcher at Ghent University, but it's a beautiful example of that Las Vegas party of bacteria on the top being kept away from those really beautiful sensitive cells at the bottom. So this system works well. Now, in the video, you heard me talk about how we can make this on a very, very common type of medical material, silicone rubber. Anytime you see a squishy, clear rubber material, that's very likely silicone. And we can actually put a mucus-mimicking layer on it very easily simply by immersing it in a compatible liquid. And because we're a little bit more technical here, I can tell you that the way this actually works is that the liquid molecules are penetrating in between the linked chains of that polymer material. And that is what gives us that liquid-like material. It's those liquid molecules are able to move around. So I also am very happy for the opportunity to show you the data that's actually backing up the claims that I made in that video. So this was an experiment where we actually treated some of that silicone material and then we stuck it in a beaker with this bacterium here. This is called Pseudomonas aeruginosa, and it is a huge problem in hospitals. It is very, very good at sticking to things, and when it does, it loves to grow. So we actually put our treated material into a solution that was absolutely packed with these bacteria, and we let a pump just pump this around for 24 hours. Now, I'm going to show you a picture, and in this picture, you're going to see that I have half of the tube treated and half untreated. I've stained the bacteria purple. Let's see if you can tell which side was which. This was the sample that came out of our experiment. And as we started to look a little bit more with some microscopy and fluorescence, we could see that on the side where we didn't have that mucus mimicking layer, we had a ton of bacteria, as you can see, very dark purple. And on the side that was treated, significantly less. Now, in biomedical engineering, which is what I do, we have a saying that you can do anything on a lab bench, but all bets are off until you try it in a living system, because we are so beautifully complex that we could never simulate all the potential things that are going on in a living system. So we needed to try this in an actual living system. So I don't have the capacity to do that myself. I'm an engineer, but I'm very lucky to have some amazing biology collaborators at the University of Notre Dame who have one of the world's best models of catheter-associated urinary tract infections. So they're very good at looking at bacteria sticking to things in living systems. So we sent them some samples, and this is the first thing that they sent back to us. Now there on the left, you see the samples that were not treated. Those were our controls. You can see that my collaborators, Professor Ana Lydia Flores Morales at the University of Notre Dame, was looking at protein adhesion, which it turns out is a critical component in setting the stage for bacterial adhesion, as well as adhesion of E. coli. And then at the bottom there, you can see the two just on top of each other to see where they're located. Then on the right-hand side, you can see when we have our liquid-infused material. Wow. These were amazing, but this is just a visual image. Let's look at the quantification. What you're looking at is the amount of bacteria, so colony-forming units, CFUs, on the y-axis, and on the x-axis, you can see the different places where these bacteria were measured: the bladder, on the catheter itself, kidney, spleen, and heart. here stands for unmodified. This was the material before we did anything. And then Li is liquid infused. The stars at the top signify statistically significant differences. Now, this may not look like much, but keep in mind that that y-axis is a log scale. These results were absolutely jaw-dropping. My collaborator, who's an expert in this, said she had never seen anything work as well as this, and we are currently in talks with one of the major global suppliers of urinary catheters to see that we can get this out to help people because of what we saw here. Now, this was E. coli, but I've got to tell you another thing that gets us excited. We tried 6 different pathogens, 6 of the most notorious organisms in hospitals. And the bottom one, Candida albicans, folks, that's a fungus. That's really good because it turns out that we have lots of antibiotics for bacteria, but when it comes to treating fungi, we have very, very few options, and they're starting to develop resistance as well. So these were very, very exciting results, and we're moving forward with them. But as I mentioned in the video, we're not satisfied with stopping there. If you think about you and your materials are able to communicate dynamically with the rest of you through a vascular system, which can bring information to your cells and take information away from your cells. And we asked, could we have these materials do the same thing? Could we engineer a communication loop where we can sense what microorganisms, what bacteria are there, and then actually respond to them in real time and direct them to do what we want them to do? Well, I wouldn't be here if the answer was no. The answer was, in fact, yes. There's an example of the 3D printing you heard me mention, where we can actually 3D print an empty vascular network into a variety of materials, silicone, rubber, or polymers that are water compatible. And when we did this, we could actually begin to sense the bacteria. So we started just by looking at how many bacteria were growing. If any of you have experience in bacteria microbiology, you're going to recognize this as a growth curve. On the bottom, you have time that the bacteria are growing, and on the y-axis, you have the number of bacterial cells. And you see that the bacterial cells, they have a lag phase. They don't do anything for a while, and they start growing exponentially, and then that sort of levels off. This is the information that you get from destructive sensing. But when we put in our vascular system, it turns out that we can see something similar without even touching the cells at all. These are 2 different methods that we use to sense the bacteria, a simple absorbance measurement there on the left, and on the right, a fancier fluid chromatography method. And you can see in the vascular absorbance plot, it looks very similar to the destructive cell count. And then in the chromatography curve, you can see that red curve. Bacterial compounds are matching the growth curve, but unexpectedly, we found that we could also see the bacteria eating. The nutrients that were there started to decline as more and more bacteria were growing. So this was the way that we could use this embedded vascular network to sense the bacteria. And then finally, by controlling how we made the vascular network, we could actually control how the bacteria were growing on the surface. This is when I say we're giving them compounds that are affecting them and telling them what to do. So this was a channel system that we set up to be able to grow the bacteria in circular points. For example, to measure the effects of compounds where you don't want one compound to affect another. So I asked my students to make me some bacteria polka dots. And what they did was calculate exactly where we needed the vascular channels to be and not to be. And then when we grew the bacteria on the surface and filled the channels with a compound directing the bacteria to not grow, they didn't. And we were able to control where they grew and where they didn't. Right, so we're very excited about this work, looking forward to taking it into the future and seeing what we can do with engineering hybrid living, non-living materials. So with that, thank you all very much for your attention, and let's have dinner. Suppose I will do questions after? I'll wait for someone to tell me what to do.
Any questions?
Yes?
Yes?
Could you elaborate on your fungi work as opposed to bacteria work, which you mentioned just very briefly?
Yes. So the work with fungi was exactly the same as the work with bacteria. If you think of yeast infections, that's an example of a fungal infection. So the problem is that we have lots of fungal cells in our bodies as well. And so we were able to use the same methods, or I should say my collaborators used the same methods to be able to look at these organisms, these yeast colonizing the surface. Basically, the procedure was in a mouse model. You insert the catheter sample, and then you insert a defined number of cells, either of bacteria or yeast. And then you let this incubate for 3 days, and then you remove the materials and look to see what was sticking and look to measure where everything went. Does that answer your question?
Any more questions? If, yes, there is one more question.
You just said that this could be extrapolated to the fungi, but fungi don't respond to antibiotics.
They do not. There are specialized compounds that they do respond to, but they're starting to develop resistance to those compounds. Not to scare anyone, but yeah.
Okay. You said also you did some 3D printing. What did you do? Because at one point you said that it penetrates, impregnates into the platform that you used.
Yes, please continue. Yes.
So you actually developed a layer on top. You deposited something, and then you exposed to the medium, or you actually allowed. What is that stuff that entered into the network?
I'm so happy you asked this question because I only had 10 minutes, so I couldn't go into detail. But what we actually use here is fugitive ink 3D printing. It was actually developed by Jennifer Lewis at Harvard University, an absolute pioneer in 3D printing. And the concept is that you can actually print into a liquid material a compound which will change, it's a solid when you print it, and then when you change the temperature, generally that will solidify the matrix around it, and it will turn the ink itself into a liquid. So when we do that, we can actually pull the liquid out of the channels, and what we're left with is an empty network of vascular channels embedded within the material. Does that answer your question?
Yeah, that's very clever, because silicon is a covalently bonded network, and to penetrate that won't be that easy. But anyway, that was very clever.
Yeah, thank you.
One more question?
Okay, as an engineer, I just have a short question for you, also as another engineer, but maybe you can answer during the dinner. What do you think? Are we humans or we are bacteria carriers? Okay, so.
That's a great question. Yeah, that's more philosophical. Let's talk about that over dinner.
Okay, any more questions?
So thank you very much for your wonderful the work. So I am from Engineering Academy of Japan. And so just follow up the previous questions, because so you had an empty region to mimic blood vessels, so inside. And have you ever thought about to putting endothelial cell to more mimic vasculature, because the internal area is fully covered with endothelial cells in the case of vasculature. So have you ever thought about that work?
Can you say that one more time with the, yes,
In the blood vessel walls?
in the empty vascular channels?
Yes.
Yes?
Yes. Have you ever thought about the putting endothelial cell to culture to cover the inside of vasculature to more mimic blood vessel walls structure?
No, I haven't. We haven't tried that, but that would be a very interesting thing to look into. Maybe we could talk more about that. If you have experience or have seen stuff like that, I'd love to get your opinion.
Time, yes.
Yes, excellent. Thank you so much.
Okay, any more question? If not, I would like to thank you very much. Thank you.
Thank you all.
Okay, I would like to thank very much all of our presenters. This means that our official agenda for today has come to an end, and I would like to invite you to the conference dinner, which will be held in a restaurant which is called Vinodol. It's conveniently located in the street of Nikola Tesla, number 10. It's within a 15 minutes pleasurable walk towards the center of the city. We didn't arrange for transportation because we expected that you would enjoy a little walk after a whole day of sitting here in the hotel. So I meet you there at 8. Thank you very much.